China has made significant advancements in bridge construction technology, with the development of innovative machinery that greatly accelerates the construction process. One such machine is the SLJ 900/32, also known as the Iron Monster. The Iron Monster is a bridge-building machine developed by the Beijing Wao Joint Machinery Company and designed by the Shijiazhuang Railway Design Institute. This massive machine, weighing in at a whopping 680 tons, completely automates the bridge-building process, saving both time and money. The Iron Monster lifts, carries, and sets prefabricated and full-length track sections at a loaded speed of 3.1 miles per hour, 5 kilometers per hour. This eliminates the need for prolonged on-site assembly processes. The machine moves via its 64 fully rotating wheels divided into 4 blocks. The Iron Monster has been used in several large-scale projects. For instance, it was used in the construction of the Yibin-Jinsha River Railway Bridge, the world's longest road-rail steel arch bridge project. Before the construction of the Yibin-Jinsha, it took 12 hours to travel between the provinces of Sichuan and Guizhou in China. Now, the estimated travel time has dropped to 3 hours. Another example is the high-speed rail project linking Inner Mongolia with the rest of China as part of China's vision of an 18,641.1-mile-long, 30,000 kilometers, high-speed rail. These advancements in bridge construction technology have played a crucial role in China's Belt and Road Initiative, which aims to link Asia, Africa, and Europe. Despite some criticisms, these inventions are still of high importance in construction engineering. The automation of the bridge construction process by the Iron Monster results in cost savings and more efficient use of resources. This is particularly beneficial for large-scale projects, such as China's Belt and Road Initiative. The Iron Monster eliminates the need for prolonged on-site assembly processes, as it can handle prefabricated and full-length track sections. This not only speeds up construction but also reduces the potential for errors that can occur during manual assembly. The Iron Monster is versatile and can be used in a variety of bridge construction projects. For instance, it was used in the construction of the Yibin-Jinsha River Railway Bridge, the world's longest road-rail steel arch bridge project. The main tower is a huge concrete structure, and was constructed by stacking blocks called segments. This process was carried out using cranes and special construction methods. The main girder suspended between the main towers is an important part that forms the skeleton of the bridge. This process posed a difficult challenge of erecting the main girder over a distance of approximately 1,000 m, the longest distance of construction over the sea in the world. The deck was laid on the main girders to create a roadway and sidewalk. Asphalt and concrete were laid on the deck to create a passable road surface. Protective fences and lighting were installed to ensure safety. Learning from the lessons of the Great East Japan earthquake. High earthquake resistance and tsunami countermeasures were implemented. The world's longest offshore construction distance was achieved in the erection of the main girders. This demonstrates the high level of Japanese bridge construction technology and was achieved by overcoming many difficulties. The bridge opened in March 2021, taking 9 years and 4 months from project start. The bridge spans Kesennuma Bay, Miyagi Prefecture, with a total length of 1,344 meters. The nickname, Kane-o-Hashi, was chosen from names submitted by the public. Kane comes from the word kaniru in Japanese, which means to fulfill hopes, dreams, and wishes. The Kesennuma Bay Crossing Bridge is expected to serve as an emergency transport route and is designed not to get flooded from tsunamis. It is a testament to the resilience and recovery of the region after the devastating earthquake.
The Girder RN09 road project in Algeria is a major infrastructure project designed to improve connectivity in rugged mountainous regions. Ozgur Insat, a leading construction company, is responsible for the construction of viaducts and tunnels in this project. The Girder RN09 road project is located in a rugged mountainous terrain with deep valleys and steep slopes. To connect geographically separated regions, the route requires the construction of multiple viaducts of great height and length. The main objectives of the project are to ensure smooth traffic flow, reduce travel time, and promote regional economic development. The viaducts are designed with pre-stressed concrete box girder structures, providing superior load-bearing capacity and long-term durability. The construction of the viaduct on the RN09 route is carried out through the following main steps. First, the terrain is surveyed in detail using lidar and drone technology to collect accurate data. On this basis, the viaduct is designed with pre-stressed concrete piers and box girders. This structure optimizes load-bearing capacity, saves costs, and is suitable for complex terrain. The construction area is cleaned with excavators and bulldozers. Then, deep concrete piles are drilled and reinforced to ensure the load-bearing capacity of the piers on weak ground. The reinforced concrete foundations are cast in place with a modern formwork system, ensuring accuracy and stability. The piers are built using an automatic climbing formwork system, helping to construct high piers quickly and safely. This system allows piers to be constructed in segments without the need for large scaffolding, suitable for construction conditions on steep terrain. The pre-stressed concrete beams were manufactured at a foundry near the construction site, then transported and installed on site. The incremental launching method was used, in which the beams were assembled at one end of the bridge and gradually pushed to the other side using a hydraulic jack system. This technique reduces the need for large cranes and ensures high precision. After installation, the bridge deck is covered with a waterproof layer and asphalt to protect the structure. A railing system, signs, and lighting were also installed to ensure traffic safety. The construction of the RN09 viaduct applied many advanced technical solutions. One of them is the use of pre-stressed concrete, with steel cables stretched inside the beams to increase load-bearing capacity and reduce deformation. Automatic climbing formwork technology allows the construction of high bridge piers accurately, even in difficult-to-access terrain. In addition, the push-pull method is an effective solution for installing long bridge girders without the need for scaffolding or large lifting equipment, minimizing construction risks. The Girder RN09 road project brings many great benefits. First, the viaducts help overcome high mountain terrain and deep valleys, shortening travel time and enhancing connectivity between regions. The bridge structure is designed to withstand heavy loads and harsh weather conditions, ensuring safety and long-term durability. Economically, the RN09 route not only improves traffic but also promotes the circulation of goods and economic development for the Girder region and neighboring areas. The Girder RN09 road project is a typical example of applying advanced construction technologies to complex infrastructure projects. With creativity and high technical skills, Ozgur Insat company completed the project efficiently, ensuring quality and progress. This is a typical project, making an important contribution to the sustainable development of Algeria. The Algeria Canal is an important irrigation project that not only helps control water flow and reduce the risk of flooding, but also supports transportation and economic development in the region. One of the key factors to ensure the durability and long-term efficiency of the canal is the asphalt paving on the contact surfaces. The asphalt paving technology applied here uses high-quality materials and modern equipment, meeting strict requirements for durability, waterproofing, and load-bearing capacity. This canal is an important traffic route, serving the transportation of goods, controlling water flow, and enhancing flood resistance. The system has a large length. The canal bed is designed to ensure durability against the impact of water flow, weather, and traffic on the canal. Before paving, the canal surface must be carefully prepared. First, road sweepers and pressure washers are used to clean dirt and mud. If cracks or holes appear on the surface, they are treated with reinforcing materials such as concrete or cement. Then, a layer of adhesive, bitumen emulsion, is sprayed evenly onto the base to increase the adhesion between the asphalt and the canal surface. The asphalt paving process is carried out using a specialized asphalt paver. The asphalt used is a mixture of bitumen and aggregate, stone, gravel, sand, heated at a temperature of 120 to 160 degrees Celsius to ensure flexibility and ease of construction. The asphalt paver with an automatic conveyor system will spread the asphalt evenly on the canal surface. At the same time, laser and GPS sensors on the machine help adjust the thickness and slope of the asphalt layer, ensuring absolute accuracy. After the asphalt is paved, The road roller will perform the task of compacting the asphalt layer. Steel wheel rollers are used to create a smooth flatness, while tire rollers will handle hard-to-reach areas to ensure uniformity. This compaction process helps to eliminate voids, increase the durability and resistance of the asphalt layer. There are three main types of machines used in the process, including 1. Asphalt spreader. This is the key equipment, with the ability to automatically adjust the thickness and slope of the asphalt layer, ensuring uniformity and accuracy. 2. Roller. Using a combination of steel wheel and tire rollers to achieve the highest compaction efficiency. 3. Bitumen sprayer. Supports spraying adhesive before spreading asphalt, creating a tight bond between the base and the asphalt layer. The asphalt spreading process not only provides a durable, waterproof and load-bearing surface, but also helps to prolong the life of the canal, minimizing maintenance costs. Thanks to that, the ALS canal not only meets technical requirements but also becomes a model in the construction of similar projects.
Ozgur Insat, a leading company of KRK Holding, was established in 1993. The company operates in fields of tunneling, transportation, infrastructure, superstructure, mining, and energy. It has proved its reliability while meeting the expectations and the needs of the projects carried out with technological solutions within the scope of correct methods and international quality standards. Ozgur Insat has achieved international success with its own financial strength, human resources, wealth of machinery and equipment as far as its experience and know-how. Domestically, the company has taken part in major parts of Metro Istanbul while completing various projects for municipality of Istanbul, such as For Levent, Taksim Metro Line, Kadıköy Kartal Metro Line, Taksim Yenikapı Metro Line, Taksim, Kabatas Funicular System construction, and multiple sewage tunnels for Istanbul Water and Sewerage Administration. Ozgur Insat has completed Black Sea Highway/Nefise Akselik Tunnel construction between Perşembe Bolaman for General Directorate of Highways KGM, Izmir Light Rail System construction, Uşyol Station project for the municipality of Izmir. Extending its operations in Algeria, Ozgur Insat has signed various successful contracts abroad. In Algeria, Ozgur Insat currently has 6 ongoing projects, besides the 3 projects are already completed. The company has increased its reputation and prestige while realizing new projects with the world's largest, well-known, and reputable international contracting groups. Tizi Uzun Ued IC Railway Project for ANESRIF and Bajaya Highway Tunnel Project for Public Works Department, Bajaya, were completed. Thenia Tizi Uzun Railway Project, El Afran, Kimis Miliana Railway Project, Thenia Borjbu Araridge Railway Project for ANESRIF, Kerata Motorway Project for Public Works Department, Bajaya, and Tizi Uzun Highway Project for Algeria Highways Administration, ADA, are ongoing projects. Ozgur is also involved in the construction of 2 solar power plants with capacities of 362 MWP and 82 MWP, supporting Algeria's energy transformation policies. Ozgur's extensive portfolio showcases their capability to handle diverse and complex projects across different sectors and countries. One of the most dangerous projects they involved is the RN09. The RN09 Karata Gorges Road project is a significant infrastructure development in Algeria, connecting the provinces of Bajaya and Sétif through a challenging 7.6-kilometer stretch of road. Ozgur Insat is collaborating with a local partner, Sarl Mediterranean Migros, to execute this project. The Notice to Proceed, NTP, was issued on July 4, 2024, with an estimated completion time of 16 months for the first phase, involved several complex engineering feats due to the difficult terrain. The project includes the construction of viaducts using steel beams on concrete footings. These structures are designed to span the gorges and provide stability. Special engineering structures known as half-bridges were also constructed to navigate the steep and split rock formations. 4 tunnels were built, totaling 1,550 meters in length. These tunnels help bypass the most challenging sections of the gorges. The existing narrow road, originally built by the French in 1865, was widened to accommodate modern traffic. This involved significant road widening with steel beams and the construction of retaining walls to ensure safety. A section of the road is being widened using steel beams over a distance of 540 meters. This widening will improve traffic flow and reduce congestion. Retaining walls are being constructed over a length of 600 meters to stabilize slopes and prevent landslides. A unique cantilever design, extending 2 to 5 meters towards the streamside, was implemented using pre-tensioned beams called estacade. This design helps manage the steep slopes and provides additional road stability.
The Girder tunnels, originally completed in 1985, are being modernized to meet European standards. This includes electromechanical works and redesigning to handle current traffic intensity. The project also faces several significant challenges. The Girder Gorges area is characterized by rugged terrain and complex geological formations, which can complicate construction efforts and require specialized engineering solutions. Environmental considerations are crucial, as the project must minimize its impact on the surrounding natural landscape and ecosystems. Ensuring the safety of workers and travelers during the renovation of the tunnels is a major concern. This includes managing traffic flow to prevent disruptions and accidents. Implementing modern safety features in the tunnels, such as advanced ventilation and fire suppression systems, is essential but challenging. The construction of viaducts and special engineering structures like half bridges and open-box culverts requires precise engineering and execution. The use of pre-tension beams, known as estacade, involves complex engineering to ensure stability and durability. Coordinating between multiple stakeholders, including local authorities, contractors, and suppliers, can be challenging, especially in a project of this scale. Ensuring timely delivery of materials and equipment to the remote project site requires efficient logistics management. The project must comply with European standards for tunnel safety and construction, which involves rigorous testing and quality assurance. Navigating regulatory requirements and obtaining necessary permits can be time-consuming and complex. Despite these challenges, the project aims to significantly improve the infrastructure and safety of the RN09 highway, benefiting the region's connectivity and economic development. Estacade beams, also known as pre-tension beams, are a type of structural element used in construction to provide support and stability, particularly in challenging environments like the Girder Gorges. Estacade beams are pre-tensioned, meaning that the steel tendons within the concrete are tensioned before the concrete is cast. This process enhances the beam's strength and load-bearing capacity. These beams often function as cantilevers, extending horizontally and supported at only one end. This design is particularly useful in areas where traditional support structures are difficult to implement, such as over streams or gorges. The pre-tensioning process not only increases the beam's strength but also its durability, making it suitable for long-term use in harsh environmental conditions. Estacade beams are commonly used in bridge construction, elevated roadways, and other infrastructure projects where robust and reliable support is needed. The pre-tensioning process allows these beams to handle greater loads compared to non-pre-tensioned beams. The increased strength of pre-tension beams can lead to a reduction in the amount of concrete and steel required, making the construction process more efficient. The tensioning process helps to minimize cracks and other structural issues, ensuring a longer lifespan for the construction. The process of pre-tensioning requires precise engineering and specialized equipment, which can increase the complexity and cost of installation. While durable, these beams still require regular inspection and maintenance to ensure their continued performance and safety. Estacade beams are a critical component in modern construction, providing the necessary support and stability for complex infrastructure projects like the RN09 Girder Gorges Road project. The RN09 project incorporates several innovative construction techniques to address the unique challenges of the terrain and ensure the project's success. Here are some notable methods. 1. Advanced tunnel renovation techniques. The tunnels are being modernized with state-of-the-art electromechanical systems, including advanced ventilation, lighting, and fire suppression systems to enhance safety and efficiency. Given the region's seismic activity, the tunnels are being reinforced to withstand potential earthquakes, ensuring long-term durability and safety. 2. Special engineering structures. The construction of viaducts involves the use of steel beams on concrete footings, providing robust support across the gorges. Half-bridges and open-box culvert structures are designed to navigate the challenging terrain, allowing for efficient water drainage and stability. 3. Pretension beams. As previously mentioned, these beams are pretensioned to enhance their load-bearing capacity and durability. They function as cantilevers, extending over the gorges and providing stable support without the need for extensive ground-based foundations. 4. Innovative construction materials. The use of high-performance concrete ensures greater strength and durability, essential for the harsh environmental conditions of the Girder gorges. To combat the effects of weather and environmental exposure, materials that resist corrosion are being used extensively throughout the project. 5. Environmental and safety measures. The project employs eco-friendly construction practices to minimize environmental impact, such as controlled blasting techniques and careful management of construction waste. These innovative techniques not only address the specific challenges of the Girder gorges but also set a benchmark for future infrastructure projects in similar terrains.
The new Osborstown underpass, located on the mainline railway line between Cork and Dublin near Sallins, is part of Kildare County Council's efforts to upgrade and improve transport infrastructure in the area. The project aims to improve connectivity and safety in the area. The underpass was constructed under the existing railway line without causing major disruption to rail operations. The main construction method used was the box-jacking method, a modern and efficient solution for works under railways. The box-jacking method is a modern construction technique in which a concrete structure, usually a box, is precast near the installation site and then pushed into its final position using a hydraulic jacking system. This method reduces on-site construction time and minimizes disruption to rail operations. Let's take a closer look at the box-jacking process. The first stage involves carefully excavating the area where the tunnel will be located. This requires careful planning and execution, especially when close to an active railway line. Ground stabilization techniques may be used to ensure the safety and stability of the excavation. Once the excavation is complete, a reinforced concrete slab is constructed. This slab acts as the foundation on which the tunnel structure will be built and provides a smooth, level surface for the lifting operation. The tunnel structure itself is a reinforced concrete box, constructed in adjacent sections. These sections are cast in formwork, incorporating reinforcement designed to withstand the stresses of the lifting operation and the future loads of the railway and road above. High-quality concrete is essential to ensure the long-term strength and durability of the structure. Each section is thoroughly inspected for quality and dimensional accuracy before being transported to the construction site. Once the foundation slab has cured, the lifting system is installed. This typically consists of hydraulic jacks placed against posts at the receiving end of the excavation. A sliding system, often incorporating low-friction bearings or rollers, is placed between the foundation slab and the concrete box sections to facilitate smooth movement. Lubricants are used to minimize friction and ensure controlled movement during the lifting process. The precast concrete box sections are pushed forward into the excavation area using hydraulic jacks. This process is carefully monitored and controlled to maintain alignment and prevent any unwanted stresses on the structure. As each section is jacked into place, the next section is connected to it, creating a continuous tunnel structure. The jacking process continues until the entire tunnel is in its final position beneath the railway tracks. Once the tunnel is installed, the void around the structure is carefully filled with compacted material to provide support and stability. The area above the tunnel is then restored, usually by replacing gravel and railway tracks. Finally, tunnel entrances are constructed, connecting the new structure to the existing road. This may include the installation of drainage, curbs, and pavements. The box jacking method offers several distinct advantages. First of all, it allows construction to be carried out without interrupting traffic on the railway line. On-site construction time is reduced by precasting the structure, while the quality and accuracy of the construction are guaranteed to be higher than with traditional methods. The method also reduces the risk of work accidents by performing complex operations under better controlled conditions. This project demonstrates the efficiency and effectiveness of the box jacking method in the construction of tunnels under critical infrastructure such as railways. The new Osborstown Tunnel will improve traffic flow and safety in the area, reduce congestion, and provide a vital link for the community. The Manjong River Bridge, Section 3-3 of the Honam High-Speed Railway Project, Korea, is an important project that plays a role in connecting key traffic routes, while optimizing the time and cost of transporting passengers and goods. To construct this bridge, the precast segmental method, PSM, was applied due to its outstanding advantages in terms of progress, quality, and safety. Why PSM? The PSM approach is chosen for several reasons, especially in challenging environments like this river crossing. Casting segments in a controlled factory environment ensures higher concrete quality and precision, minimizing on-site variations. Precasting allows for concurrent segment production and foundation work, significantly accelerating the overall project timeline. Minimal on-site casting means less noise, dust, and waste, minimizing the environmental impact and disruption to surrounding areas. Factory production and mechanized installation processes reduce the need for working at height, improving overall site safety. The box girders are the heart of this bridge. They are manufactured in a dedicated precasting yard using steel formwork. Precisely engineered steel forms create the desired shape and dimensions of each segment. High-strength steel reinforcement is meticulously placed within the formwork according to design specifications. Concrete is mixed at a standard ratio to ensure strength, then poured into molds and vibrated to remove air bubbles. After casting, the beam sections are cured to achieve the required concrete strength, usually for 28 days. Throughout the casting process, rigorous quality checks are performed, including concrete strength tests, dimensional checks, and surface inspections. After sufficient curing, the formwork is removed, revealing the finished box girder segment. Transporting these massive segments requires specialized equipment and meticulous planning. Heavy-duty trailers designed for transporting oversized loads are employed. Detailed route surveys are conducted to identify suitable roads and bridges capable of handling the weight and dimensions of the segments. The box girder is securely fixed on the vehicle, avoiding vibration or impact during transportation. Transport operations are often carried out during off-peak hours and require police escorts and traffic management to minimize disruption. The star of the on-site installation process is the launching gantry, a massive, self-propelled structure specifically designed for placing the precast segments. The launching gantry is assembled and positioned on the completed piers. The gantry's lifting system carefully hoists each segment into position. Hydraulic jacks and alignment systems ensure precise positioning of the segments. Post-tensioning tendons are then threaded through ducts within the segments and stressed, creating a continuous, strong structure. Once a segment is secured, the launching gantry advances forward to the next position, ready to receive and place the next segment. This process repeats until the entire span is completed. After all segments are placed, the gaps between segments are filled with grout to ensure a monolithic structure. A concrete deck slab is cast on top of the box girders to form the roadway. Safety barriers, drainage systems, and other necessary elements are installed. The PSM approach allows to construct the Manjong River Bridge efficiently while minimizing environmental impact and maximizing safety. The precast segments ensure high quality and durability, while the launching gantry allows for rapid and precise installation. The result is a strong, resilient, and aesthetically pleasing bridge that will serve the Honam high-speed railway for decades to come. The precast segmental method, PSM, is an advanced technology applied in bridge construction, especially in large projects that require fast progress and high quality. The highlight of this method is the use of reinforced concrete or pre-stressed concrete beams precast at the factory or casting yard near the construction site. After completion, these beams are transported and assembled on site through a pre-stressed cable system and epoxy glue. The PSM precast span method offers many outstanding advantages. The production of beams at the factory saves time and ensures consistent quality. At the same time, this method also minimizes the impact on the surrounding environment such as noise, dust, and traffic in the area. In addition, the construction process is carried out according to standardized procedures, ensuring higher labor safety than traditional methods. However, PSM also has some limitations that need to be noted. The initial investment cost is quite high, requiring modern equipment and casting plants along with a team of skilled technicians. Transporting large girder sections can be difficult in areas with limited traffic conditions. In addition, the installation process requires high precision. If errors occur, it will greatly affect the progress and quality of the project. The PSM method has been successfully applied in many large projects around the world such as the Millau Bridge in France, the Han River Bridge in Korea, and many highway overpass projects in China and Vietnam. Thanks to its ability to save time, ensure quality, and optimize labor safety, PSM is considered an effective solution for large bridge projects today.
Connecting Rusky Island and the Russian peninsula and Vladivostok, the Rusky Island cable-stayed bridge is the longest cable-stayed bridge in the world today, with its main span of 1,104 meters between A-shaped pylons of 320 meters in height. It provides a 70 meters high navigational clearance through the Bosphor-Vostochny Straits, thus symbolizing the new gateway to Russia in the Far East. It is also a bridge of records, i.e. cable-stayed span length, tallest pylons, longest stay cable, and shortest construction time. The general arrangement and description of the main components of this exceptional structure and its stay cables, which have been the subject of special care in order to improve the bridge response and durability, are presented, and, more particularly, the stay cable technology that uses compact parallel strand cables. Finally, the project construction and methods that were used to help its completion in less than 4 years in the harsh eastern Siberian climate are presented with a focus on safety. This titanic yet symbolic project mobilized an army of both native and French designers, engineers, and builders to work on the Golden Horn cable-stayed bridge, 737-meter central span, spanning the bay in the center of Vladivostok, and the Rusky Bridge, which crosses the eastern Bosphorus Strait and links the Nazimov Peninsula to Rusky Island, making Vladivostok the home city of 2 major cable-stayed bridges amongst the 10 longest in the world. The Rusky Bridge over the eastern Bosphorus Strait boasts a total length of 1,872 meters. It features 384-meter side spans and a 1,104-meter cable-stayed central span, which beats the previous record holder, the Sutong Bridge in China, by 16 meters for this type of structure. The navigational clearance is 450 meters in width and 70 meters in height. The central span is supported by 2 lateral planes of stay cables anchored to the tops of the 319-meter-high A-frame pylons. The pylons stand on 2 13-meter-high reinforced concrete pile caps that are linked together with a tie beam and supported by 240 piles with a diameter of 2 meters in lengths, varying from 20 meters to 65 meters, anchored in the bedrock. The stay cables are anchored to the top of the pylon in anchorage boxes, which are steel structures fixed to the concrete using studs. The deck, which has an upside-down airplane wing shape, has a total length of 25.96 meters and a height of 3.20 meters. Its central span is made from an orthotropic steel box that stretches for 70 meters beyond the towers and the side spans. Due to the position of the first stay cable, located at 53 meters on either side of the tower's axis, the steel section in the back span had to be extended to maintain the equilibrium. The steel deck represents 67% of the bridge's total length. The deck of the central span is built by cantilevering segments of both 12 meters and 24 meters in length. The side spans stand on reinforced concrete piers and abutments, and vary in length from 60 meters to 84 meters. In the concrete section of the side spans, the deck is a multicellular pre-stressed concrete box girder, with 2 0.6 meter thick side vertical webs and a 0.4 meter thick central web in the main run. The upper and lower slabs have a standard thickness of 0.3 meters. The stay cable system used on the Rusky Bridge is Freycinet's proprietary parallel strand and compact system. Compact stay cables included individually protected strands that are placed in a parallel fashion inside an outer sheath. Each strand features 7 galvanized wires protected by a wax film and a high-density polyethylene HDPE sheath that is directly extruded on the strand in the factory after the wax has been applied. When building bridges with very large spans, the drag force caused by the wind becomes the most critical factor when sizing the towers and their foundations, meaning that every effort must be made to reduce the drag force to a minimum. To achieve this aim, Freycinet has masterminded the compact stay cable technology that, unlike other technologies, allows more strands to be fitted inside the same diameter sheath, thereby reducing drag by around 25%. In the deck and the pylon heads, each strand is individually anchored using custom-designed wedges in anchorages featuring patented devices that ensure the strand's fatigue resistance and minimize unwanted stresses due to cable movements. Furthermore, Freycinet's anchorages are fitted with a system that guarantees a perfect seal. The exposed parts of the strands and the internal parts of the anchor block are injected with wax to protect against corrosion. Thanks to all of these devices and systems, combined with corrosion protection for the external metal parts of the anchorages, Freycinet's stay cable system offers unrivaled durability. Construction works on the bridge were carried out over a 47-month period. The construction works could only be completed within such a short time by working 24 hours a day, 365 days a year, The design of Freycinet's compact stay cable system used for the Rusky Bridge came in for close scrutiny to ensure that the cables would withstand the harsh conditions in the Primorsky Krai region, marine environment, sub-zero temperatures down to -30 degrees Celsius, high wind speed during construction, etc., while meeting the project's major technical requirements. The ease of installation, while maintaining the required production output, was ensured with the use of light plant equipment to improve the process of installing the steel segments and suitable fitting methods and tensioning tools geared towards the long stay cables used, while minimizing installation times. To comply with the extremely tight schedule for such a major feat of engineering, a dedicated technical structure had to be set up and incorporated into the Vladivostok work crew in order to promptly meet the need for suitable execution methods. Freycinet developed new equipment for the installation phases that could be used for working in low temperatures, especially since stay cables could be fitted at any time of day or night in temperatures down to -30 degrees Celsius. To work around the schedule constraints, the installation methods were redefined, particularly the process for lifting long stay cable ducts. The aim was to guarantee the worker's safety when lifting the longest ducts to a height of 320 meters, while guaranteeing the duct's integrity, bearing in mind that having to replace any ducts would put work significantly behind schedule. Stay cables had to be installed around the clock without any interruptions, meaning that a safety plan was needed to minimize the risks associated with installing the stay cables, working at night, and working in extreme weather conditions, since the apparent temperature could fall below -30 degrees Celsius depending on the wind speed. Furthermore, the eastern Bosphorus region is prone to abrupt changes in visibility and wind, with the likelihood of sudden swirling gusts of wind, especially on the island. Risk analysis and training formed the backbone of the quality and safety management system throughout the stay cable installation process. The risk analysis highlighted the operational difficulties and risks inherent in working in cold conditions and at night. 3 types of risks were analyzed: equipment risks, related to equipment failure without any effect on project progress; operational risks, affecting the progress of the installation phase; human risks, related to operations in the environment. The findings were used to create the best possible working environment and reduce the impact on the work cycle. The study also helped ensure that the appropriate resources were provided for carrying out work both safely and efficiently. Because of the operational difficulties and risks inherent in working in cold conditions and at night, new methods and resources were developed to keep the pace with the project's high work rate. Technical training specific to the project also had to be developed and delivered. In all, 200 hours of training divided into 88 sessions were given. A detailed review was conducted into each workstation, especially those outside the tower during the strand hoisting phase, and a specific set of procedures was defined accordingly. One such procedure was the requirement for people to work in teams of 2 or more, the idea being for each member to watch the other for any warning signs of cold weather exposure. Heated shelters were also set up on the platforms to allow teams to work in shifts. By July 2012, and right on schedule, the stay cables had been installed, the dampers fitted, and the stay cable monitoring system implemented, all of which without a single accident. The bridge opened to traffic in September 2012. Adi Batan, also known as PT Adi Persada Batan, is a subsidiary of PT Adi Karya Persero Tbk. Established in December 2013, Adi Batan specializes in the production of precast concrete products. Adi Beton produces a wide range of precast concrete products, including spun piles, square piles, CCSP, continuous cast spun piles, FCSP, full-form spun piles, girders, box culverts, PPCP, pre-stressed precast concrete piles, jacking pipes, barrier walls, pier heads, half slabs, and more. The company operates several factories and batching plants across Indonesia, including locations in Java, Sumatra, and Kalimantan. Adi Beton has been involved in numerous major infrastructure projects, such as the Bali Mandara Toll Road, the Tanjung Priok Port Rehabilitation, the LRT Jabodebek project, and the Sigli Banda Aceh Toll Road. Adi Beton is known for its commitment to quality and innovation. The company has received various awards and recognitions for its contributions to the construction industry. Adi Beton plays a significant role in Indonesia's construction industry, providing durable and reliable precast concrete solutions for various infrastructure projects. They employs advanced techniques and stringent quality control measures to produce high-quality T-walls and girders. About T-walls, Adi Beton's engineers design T-walls based on specific project requirements, considering factors like load-bearing capacity, dimensions, and reinforcement. Detailed design drawings are created to guide the production process. Specialized formwork is constructed to shape the T-wall, ensuring precise dimensions and smooth surfaces. The formwork is typically made of steel or aluminum, allowing for easy assembly and disassembly. Reinforcement bars, including longitudinal and transverse bars, are carefully placed within the formwork according to the design specifications. The reinforcement provides structural integrity and tensile strength to the T-wall. High-quality concrete is mixed using precise proportions of cement, aggregates, water, and admixtures. The concrete mixture is poured into the formwork, ensuring complete filling and proper compaction to eliminate air voids. The concrete is cured to achieve the desired strength and durability. Curing can involve various methods, such as steam curing or water curing, depending on the specific requirements. Once the concrete has cured sufficiently, the formwork is removed and the T-wall is inspected for any defects. Any necessary finishing work, such as smoothing surfaces or applying protective coatings, is carried out. Throughout the production process, rigorous quality control measures are implemented to ensure adherence to design specifications and industry standards. This includes testing the concrete strength, inspecting the reinforcement placement, and verifying the overall dimensions and tolerances. The production of girders at Adi Beton follows a similar process, with some specific considerations. High-strength steel tendons are tensioned within the concrete to induce compressive stresses, increasing the girder's load-bearing capacity and reducing deflection. This pre-stressing process is a critical step in girder production. Girders can be produced in various shapes and sizes, depending on the specific project requirements. Common girder types include I-beams, T-beams, and box girders. Once the girders are cured and inspected, they are transported to the construction site using specialized equipment. The girders are then carefully lifted and installed into place, often using cranes or other heavy lifting machinery. By adhering to strict quality control standards and utilizing advanced production techniques, Adi Beton ensures that their T-walls and girders meet the highest standards of quality and durability. The specific erection assembling method used can vary depending on the project, site conditions, and girder design. However, here are some common methods used by Adi Beton. 1. Crane method. The construction site is prepared, including the erection of temporary supports or scaffolding. The precast girders are transported to the site and positioned near the bridge piers. A large crane is used to lift each girder and carefully place it on the bridge piers. The crane operator must ensure precise positioning and alignment of the girder. Once the girder is in place, it is connected to the adjacent girders using steel connectors or other appropriate methods. The connections are designed to transfer loads efficiently and ensure the structural integrity of the bridge. 2. Launching gantry method. A gantry crane is assembled on the bridge abutment. The gantry crane lifts and places precast concrete girders onto the piers. The gantry is then moved forward to the next pier, and the process is repeated. Advantages of this method are suitable for long-span bridges and can be used in various terrain conditions. However, disadvantages requires significant construction space and time for gantry assembly and dismantling. 3. Self-propelled modular transporter, SPMT method. Precast concrete girders are transported to the construction site on SPMTs. The SPMTs are used to lift and place the girders onto the piers. Advantages are flexible, and can be used in various site conditions. But disadvantages are also require specialized equipment and skilled operators. Adi Beton prioritizes safety throughout the erection process, implementing strict safety protocols and providing training to workers. Accurate positioning and alignment of girders are crucial to ensure the structural integrity of the bridge. Adi Beton strives to optimize the erection process to minimize downtime and maximize productivity. Rigorous quality control measures are implemented to verify the quality of the erected girders and their connections. By employing these methods and adhering to strict quality control standards, Adi Beton ensures the successful erection of precast concrete girders for various bridge projects.